Hypothesis testing can be really confusing. Hypothesis testing, we're going to break it down into small pieces and hopefully it'll make sense by the end of this live stream. StatQuest. Bam! Hello, I'm Josh Starmer and welcome to the StatQuest live stream. We've got people watching in Uruguay, in Peru, looks like Bangkok, India, New York City, more India. Got all kinds of people watching, and so that's super exciting. Today we're going to be talking about hypothesis testing, which is one of those basic fundamental concepts in statistics that always seems backwards. And I'm hoping that we can kind of break it down into small pieces, and we'll see that it actually kind of makes sense once you see the small pieces. All right. So with that said, I see we got some people from Virginia and Mexico. We got some Brazil, which is really exciting. And so I've got a couple announcements to make. So we're gonna make a few announcements. In June, we're going to do webinars on support vector machines in Python from start to finish. I'm really excited about this. The response for the decision tree StatQuest was really exciting. And so we're just gonna keep going, and we're gonna cover new topics. So this month we're gonna do support vector machines. I should announce the dates soon in the next couple of days. So check the StatQuest community blog. I'll also post it on LinkedIn as well. So check those spots if you wanna check things out. I've also got some new study guides out, which I'm really excited about. We've got a new linear discriminant analysis study guide. It's 5 pages of total awesomeness. And that gives us a BAM. And we also have Gaussian naive Bayes, which is 7 pages of total awesomeness. Double BAM. So we're going to talk about hypothesis testing. I see a bunch of more people have signed on, so I want to give them a shout out because it's really exciting to have a big crowd. We got a lot more people from India. We've got someone from Indiana. We've got more Brazil, Malaysia, China, France, more Brazil, Brazil, Colombia, BAM from Mumbai, Iran, Serbia, Istanbul, Germany, more Indonesia, Egypt, Bulgaria, all kinds of places. So we've got a bunch, and more people from Mexico, and more Colombias, and Denmark, holy smokes, Washington. Anyways, we've got everything covered. Well, not everything. We got Nepal and Pakistan. We got a lot of places covered, including Delaware. So let's just move on with hypothesis testing, because we've got a lot to cover, because this is one of those confusing topics that I hope to demystify, and hopefully you'll have it for the rest of your life in your head. Okay, I'm not going to name any names, but imagine there was a virus, any virus, and that we had 2 drugs that we could use to treat it. So we give drug A to 3 people and measure how long it takes each person to recover from the virus. Beep, boop. The first thing we notice is that not everyone recovered in the exact same amount of time. Person number 1 recovered the fastest, and person number 2 recovered the slowest. It's possible that person number 1 eats healthy food and exercises and already has a strong immune system, and that helped them recover quickly. And maybe person number 2 doesn't get as much exercise. Or maybe person number 2 has a stressful job or lives where there's a lot of air pollution, or there's some other reasons why maybe they're just not as healthy as person number 1. The point is that even though all 3 people had the same virus and took the same drug, they did not all recover in the exact same amount of time. And that might be due to a lot of random things like exercise or job stress. And these are things we cannot control. Now let's give drug B to 3 different people that have the virus and measure how long it takes them to recover. Again, we see that even though 3 people had the same virus and took the same drug, they did not all recover in the exact same amount of time. And this is probably due to random stuff that we can't control, like how much exercise each person gets or how much candy they eat. But overall, it looks like people taking drug A took less time to recover than people taking drug B. And when we calculate the mean or average for drug A and the mean value for drug B, we see that, on average, there's a 15-hour difference between drug A and drug B. So, after seeing this preliminary data, it might seem reasonable to form the following hypothesis. People taking drug A need, on average, 15 fewer hours to recover than people taking drug B. And now that we have this hypothesis, we can test it. And the way we test it is by repeating the experiment. I got to put this ukulele down. I'm starting to make a lot of racket with it. Okay. Now, when we calculate the means, we see that on average, people taking drug A need almost 35 more hours than people taking drug B. Compared to our preliminary data, this result is very unexpected. In fact, it is the opposite of the original hypothesis. But it's also possible that all 3 people that took drug A in the second experiment have super stressful jobs and unhealthy lifestyles. And maybe that's why it took them so long to recover. And maybe everyone taking drug B was well rested and super healthy to begin with. And maybe that's why they recovered so quickly. But it's also possible that maybe we mislabeled drug A and drug B and did the wrong experiment. So we repeat the experiment, and again, the results are totally backwards from the preliminary experiment, and totally backwards from the hypothesis we made. So again, just to make sure we didn't mislabel things, we redo the experiment, and again, these results are the opposite of the original hypothesis. Hypothesis is one of those weird words where it's hard to know like what the plural is and what the singular is. There's just a lot of S in that word at the end. So it's easy to get it confused. Okay, anyways, we just keep repeating the experiment, each time double checking every little detail. Beep, beep, boop, beep, 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 beep. And every time we do the experiment, we get the opposite result of the original hypothesis. So, after doing all of these repeated experiments where we double-checked every little step, we can confidently reject this hypothesis that we came up with after doing the preliminary experiment. Bam. Bam! I got ahead of myself. Okay, since we just covered a super important point about hypothesis testing, let's summarize it. We collected some preliminary data. We used that data to form a hypothesis about the difference between drug A and drug B. Then we did a bunch of follow-up experiments, and they gave us an overwhelming amount of evidence that suggested the hypothesis was wrong. So we rejected the hypothesis. And then we said, bam! All right, now let's imagine these extra experiments never happened. And go back to the original preliminary experiment and hypothesis. Now, just like before, we decide that this test... Now, just like before, we decide to test this hypothesis by repeating the experiment. Only this time, instead of getting something that's the exact opposite of what we expected, we get something that's slightly different. In this case, the difference is in the same direction, but is only 12 hours. Then we repeat the experiment again, and again, we get something slightly different from the preliminary experiment and hypothesis. The difference is in the same direction, but this time the difference is 19 hours. So the good news is we probably didn't mislabel the drug like we did last time. And the differences between the three experiments might be due to random things we cannot control. Like maybe these people exercised a lot and had relatively healthy diets compared to these people who took longer to recover. But regardless, the hypothesis says people taking drug A needed 15 fewer hours to recover. But when we repeated that experiment, the first replicate said the difference between averages was 12, which is different from the hypothesis. And the second replicate said the difference was 19 hours, which is also different from the hypothesis. And let's be honest, the only reason the hypothesis says 15 fewer hours is because that was the result from the first experiment. However, we could have just as easily put 12 fewer hours in the hypothesis because that's what we got the second time. Or we could have put 19 fewer hours in the hypothesis because that's what we got the third time. So, if we just pick one experiment, like the first one, and use that to define the hypothesis, then we have two experiments that are not different enough to give us confidence to reject the hypothesis. But because there is just as much data suggesting that the difference is 12 hours, and there's just as much data suggesting the difference is 19 hours, these experiments don't make us super confident that the hypothesis of 15 fewer hours is correct. I mean, that was just a guess. And again, maybe drug A reduces recovery by 15 hours, but maybe it reduces recovery by 12 hours or 19. Because the results from the repeated experiments are not different enough to cause us to reject the hypothesis, and because they don't convince us that the hypothesis is correct either, the best we can do is fail to reject the hypothesis. Small bam. Failing to reject the hypothesis is kind of like, it's a little bit of a bummer. It's kind of a weak statement. We're just, we blew it. To summarize what we've covered so far, we can create a hypothesis, and if data give us strong evidence that that hypothesis is wrong, then we can reject the hypothesis. But when we have data that is similar to the hypothesis, then the best we can do is fail to reject the hypothesis, because that hypothesis was really just a guess, because it's unclear if that hypothesis should be based on the first result we got, or this other slightly different result, or this result, or any other possible outcome that's close to 15. So double bam. So we've learned that we can reject a hypothesis, or we can fail to reject the hypothesis. We reject because we have overwhelming data that says that the hypothesis is wrong, and we fail to reject because that hypothesis was sort of a guess to begin with, and other data suggests maybe something else similar, but not exact, could be that hypothesis. Okay, now let's take a closer look at the hypothesis itself. You may remember that the only reason the hypothesis is 15 fewer hours is that was the first result we got. But we could have just as easily gotten a 12-hour difference and ended up with a different hypothesis. Or we could have gotten a 19-hour difference and ended up with another hypothesis. And if 12 and 19 are reasonable hypotheses, then so is 15.5 or 15.00001, or 14.99999, ... In other words, there are a lot of reasonable hypotheses. How do we know which one to test? Since the goal is to see if drug A is different from drug B, we simply test to see if there is no difference between drug A and drug B. Now when we do an experiment and we get a difference of 0.5 hours, or we get a 0.5 hour difference, we know that it is possible that we could have randomly selected someone who just happens to exercise a little less than that person. And that might and that person who exercises just a little less might take a little longer to recover. And it's possible that we could randomly select someone with a slightly better diet than that person, and that person might recover a little more quickly. And since small random differences give us slightly different results, rather than worry about whether or not the difference is 0.5 or 0.25 hours, we simply see if the data convinces us to reject the hypothesis that there is no difference between drug A and drug B. In this case, the result, 0.5 hours in favor of drug B, is close to 0, but small random changes could easily result in a 0.25 hour difference in favor of drug A. In other words, the data does not overwhelmingly convince us to reject the hypothesis. So we fail to reject the hypothesis that there is no difference between the drugs. In contrast, if we tested the drugs on a lot of people, and there was a pretty big difference, and little random things would probably not change the results very much, then we can confidently reject the hypothesis that there is no difference between drug A and drug B. Double bam! Okay, terminology alert. Oh no! The hypothesis that there is no difference between things is called the null hypothesis. In summary, rather than get stressed out over a large number of possible hypotheses that we could test to see if drug A is different from drug B, we use the null hypothesis to determine if there is a difference. If we do an experiment with a bunch of people, and a lot more people taking drug A had shorter recovery times than people taking drug B, so many that it would be hard to imagine that everyone taking drug A had better diets or got more exercise than people taking drug B, then we could reject the null hypothesis. And then we would know that there is a difference between drug A and drug B. And we could estimate how different they are using measures of standard error or something like that. Alternatively, if it's hard to tell the difference between drug A and drug B because the results overlap a lot, then we would fail to reject the null hypothesis. In this case, we could do a power analysis to make sure our sample size was large enough to reject the null. Triple bam! Woohoo! The end. Okay, so we've made it to the end of this StatQuest. Let's go back to just me being big and large, and you're just going to see me looking over at the chat to see if we got any good questions. Someone just said no one knows where Calgary is. That was part of the shout out at the beginning. Someone's from Portugal. Wow. We got Poland, and some other stuff. Argentina. Holy smokes. Someone asked, should these group samples have some attributes regarding their lifestyles? What if we kept track of their diets and their exercise? And that's a great idea. And we could do that, and we would have a better experiment, and we would be better able to isolate the difference between the medications and the drugs. However, the point I'm trying to make is that even when we keep track of people's diet and we keep track of their exercise, there's still random things, like maybe their genetic makeup, or like I said, where they live, air pollution, or like I said, their jobs. There's all these like random things. There's always something else that could have an effect on how long it takes for me or someone else to recover from that illness. And because we can't make a model that includes every single thing, all those impossibly infinite things that could cause us to get a slightly different result, when we do experiments, we have to take into account that there could be some random noise in there that could change it. And if we replicated the experiment, we might get a different value. So yes, we can keep track of diet and exercise, but we have to know that there's always going to be something else that we probably cannot control. And that's the fundamental concept of statistics. If we always got the same result, if we could keep track of everything and we could say people that got this much exercise and had this job and lived in this place, they all recovered in the exact same amount of time. If they all did that, then we wouldn't even need statistics. We would just say those people recover in 5 hours or whatever, And so a fundamental thing about statistics is dealing with all those little random things that we can't include in our model, because some of the stuff we can anticipate, but there's stuff that, who knows, maybe we can't anticipate. It could be anything. There could be like some weird like gamma ray coming from a different solar system that causes something to change. And that might give us a different value. So I think that's an excellent question, because it really touches on the fundamental reason why we do statistics to begin with. What else do we have over here? We've got, someone said, so someone said, what happened earlier when we got the exact opposite? I think in that experiment, we can conclude that when we did the preliminary experiment, we had everything backwards. And so, so from that experiment, we could just kind of say we rejected the hypothesis that we generated from the preliminary thing, because we decided, we must have swapped the labels. So that was an example of rejecting the hypothesis. Someone asked if I could talk about z-scores, and I will definitely do that. I will put that on the short list. Z-scores, I'll be honest, z-scores are one of those kind of annoying things. They're a little bit of a holdover from when statistics was taught like 50 years ago, before computers. And the only way to look up p-values and stuff like that, you couldn't get a p-value to calculate it. You couldn't get a computer to calculate a p-value for you. Instead, you had to look it up in a book, and ZStatistics are related to that. And a lot of fancier statistics were developed around the time when we were using ZStatistics to look up p-values in a table rather than use a computer. And since the statistics were built back in that age, or created in that age, they use the ZStatistics as a way of sort of explaining things. And so it's sort of this relic from long ago that continues to be with us, sort of like a prehensile tail that we just carry around anyways. What else do we got? We got all kinds of stuff going on here. Western Australia, Sao Paulo, Brazil, all kinds of questions. Someone asked, do we always need to do preliminary analysis to come up with a null hypothesis? And the answer is no. That's the magic of the null hypothesis. I'll try to include that bit in the final when I make this StatQuest, when I take this live stream and I make it a full-blown StatQuest, I'll try to include that. The beauty of the null hypothesis is, because we just say the hypothesis is that there's no difference, we don't need preliminary data to suggest that. We're just going to say it. And then we'll gather data that will either reject that hypothesis or will fail to reject that hypothesis. So that's a cool thing. Instead of having to pick a hypothesis based on preliminary data, which is kind of stressful, because if we did the experiment different times, we get different values. Rather than having to deal with that, with the null hypothesis, we just state it from the get-go and go with it. What else do we got? Someone asked, what do we do when we don't know the sample size beforehand? I don't know. You need to know the sample size in order to get a good estimate. However, now that I say that, we have measurements of sort of effect size and things like that. Like imagine the standard error, which incorporates the sample size into it. So if we have a large sample size, usually that means the standard error is going to be relatively small. And so they don't tell us the sample size, but they tell us the standard errors. Then we can still do hypothesis testing based on those standard errors. What else we got? What does z-score have to do with hypothesis testing? We can talk about that in the z-score live stream, which I'm sure will come out soon, because I think that's a great kind of follow-up to this one. So hopefully that's what we do next. I can't make a promise that that's what we'll do next. Someone says, why use hypothesis testing if we could just use Bayesian credibility intervals? And that's an excellent question, and also a raging debate in all of statistics. So hypothesis testing is part of a branch that people call frequentist statistics. And there's another branch called Bayesian statistics, and we touched a little bit about Bayesian statistics in the last live stream when we derived Bayes' theorem. And they have different approaches to kind of accepting hypotheses. That's what we do in frequentist land. And in Bayesian land, they have an alternative way to deal with those problems called credibility intervals. So why do this hypothesis testing when we could do the credibility intervals? And there's a lot of reasons for that. One is legacy. Again, frequentist statistics are just sort of part of how people do statistics. That they were done earlier, and people just said, "Hey, that's what I learned. I'm going to teach that." But there's also some fundamental sort of annoying things about Bayesian statistics in that they're not always relatively easy to do, and since Bayesian statistics and frequentist statistics will often give us the same result, people will choose the easier route to get to that result. Bayesian statistics sometimes involves, not always, but sometimes involves sort of complicated what do you call a random sampling, or what's the good word for it when we're trying to simulate what would go on. So Bayesian statistics often have these relatively complicated simulations that are used to derive this credibility interval that you use to make decisions, and that can be a kind of a pain to generate, relatively speaking. Whereas frequentist statistics, we can just plug stuff into Microsoft Excel and get our p-value, and bam, we're done. And since oftentimes they'll both give us the same result, people will choose sort of the more direct approach. However, I don't want to downplay Bayesian statistics. There's a lot of cool, interesting stuff going on in there, and it's worth knowing what it's all about. We got someone from Lithuania. That's exciting. Someone asked this is a little off topic, but if I'm ever going to do a sort of diploma course, am I going to publish something on Udemy or something like that? And the answer is we're headed that direction. And I feel like if you look at the StatQuest list of videos that I have, if you go to the index that I have on the StatQuest website, there's a lot of variety there. It's because I didn't just start from the beginning, kind of work my way down. And as a result, there are gaps, in the coverage of topics. I kind of because the way StatQuest originated was someone I worked with would say, hey, Josh, I got this question. And I go, hey, I'm going to work on a StatQuest that answers your question, because that's how StatQuest started. It wasn't like, hey, I'm going to start from the beginning of statistics and just kind of build up real slow, because it was sort of like I was just answering questions as they came to me. There's a little gap. There are little gaps throughout my index and collection of videos, and I'm trying to fill those gaps. And once I fill enough of them, yes, we're going to do a StatQuest diploma, and I'm super excited about that. Someone asked about the tabla behind me. Yes, that's a tabla. So that's that. Anyways, we're at the 30-minute marker, and so it's time for me to go away. I just want to thank everyone for coming to my live stream today. I'm really excited. Like I said, we've got new study guides available at the statquest.org website, and we've got we're going to be doing support vector machines and webinars. So just stay tuned on either YouTube, on the YouTube community board, or on LinkedIn, and I will post the registration and sign up pages for those if you want to participate in those. All right, until next time, quest on.